Hi, I'm Vinay, and today I'll be talking about WisSort, external sorting for byte addressable storage. Storage is not the same anymore. Storage devices such as disk drives and SSDs are connected over PCI Express and use transistors as their persistent media. These devices usually have the following features: they are block addressed, they have good sequential bandwidth, symmetric read write performance, no concurrency complexity because a single thread or two can saturate the entire bandwidth. While these devices have served us well, end of Moore's law and new workloads like ML are demanding a more heterogeneous data center, which means new interconnects and new storage media is being introduced for better efficiency. Interconnects such as CXL and storage media such as 3DXPoint and XL-Flash have given rise to new kinds of storage devices with fundamentally different properties. Properties such as byte reducibility, good random bandwidth, asymmetric read-write performance, and a higher concurrency complexity. So, in this work, we ask, can data-intensive computation be designed to take advantage of new storage devices? In short, the answer is yes. When applications are redesigned from ground up to take advantage of the storage properties, they can be 3 to 5x faster than competing state-of-the-art approaches. In our work, we use sorting as the data-intensive application. We introduce a new model called Braid to represent the byte reducible storage characteristics. We introduce new sorting mechanisms that will help us comply with the Braid model to achieve peak performance. We implement these mechanisms in a sorting system called WisSort and evaluate it against standard sorting workloads and show we are 2 to 7x faster than state-of-the-art approaches. Sorting is widely used, from web indexing to relational databases. In fact, a recent work showed that 50% of all computer time is still spent on sorting and searching in large data centers. Now, let's imagine a file that contains a bunch of records in contiguous fashion. Each record contains fixed size keys and values. In our setup, we assume that this unsorted input file starts on the BAS device and ends on the BAS device as a sorted output file. Now, we can view this BAS device as a slower DRAM, where we make no changes to our in-memory sorting application and sort in place on the BAS device directly. So, we observed that performing highly concurrent in-place sample sort on PMEM can be 9x slower than performing highly concurrent in-place sample sort on DRAM. Now, while we take advantage of the byte reducibility and random read, we really ignore the concurrency complexity of the BAS device by doing this approach. So one way to address this would be by viewing the BAS device as a faster disk, where we make repeated copies of the key and value to the DRAM in blocks, sort it and write it back, allowing us to generate a much more concurrency-aware sorting system. This approach is definitely better than the in-place sample sort. However, this traditional external sorting system does not take care of the byte reducibility or the random read property of the device. So we introduce WisSort that takes advantage of all the new features and is aware of the eccentric aspects of the storage device to produce the highest performing sorting mechanism. Now let's quickly look at how traditional external merge sort works. Here the file starts off on the BAS device, where the keys are represented as blocks and the values as stripes. The DRAM capacity is traditionally much smaller than the BAS device, so you repeatedly read in a bunch of blocks of unsorted input file to the read buffer in concurrent fashion. You gather the keys, sort on those keys, and then write it to the write buffer along with their respective values. Once the write buffer is full, you write it back to the run file, and you repeat this step until you generate all the run files required. This marks the end of the run stage. Now, during the merge stage, you read in the first few blocks of each run file to the read buffer, find the minimum amongst the first few blocks, and then write it to the write buffer along with its value. And once the write buffer is full, you write it down to the sorted output file. You repeat this step again until you finally generate the total number of sorted output file. As you can see, in this setup, you always do sequential accesses in blocked fashion. Now that we have seen how traditional approaches work, let's now use the Braid model to guide us into a more efficient one. The model helps us understand and generalize the variety of unique characteristics offered by BAS. properties such as byte reducibility, where you can now perform granular accesses to the device. So the sorting goal must be to read only keys, as we only perform sorting on the keys. The second would be higher random read performance. Random read is on par with sequential reads on these new devices, which means you don't need to now perform only sequential reads and sequential writes. Perhaps try to use random reads of keys and values when possible. Asymmetric read-write cost, where reads can be 4x faster than writes on these new devices. So, identify ways to limit or avoid writing run files altogether. Read-write interference, where read bandwidth can degrade up to 2x when there are overlapping writes. So, separate concurrent reader and writer threads while sorting. Device constraint concurrency. Max concurrent writes can be 2x slower than peak write performance. So, manage read and write concurrency very differently. Given these sorting goals, WizSort uses 3 mechanisms to achieve braid compliancy: key value separation, interference aware scheduler, and thread pool controlling. Let's look at how each of these mechanisms work. Just like external merge sort, WizSort has 2 phases, run phase and a merge phase. During the run phase, we perform a strided gather of all the keys into the memory and maintain pointers that point to the value offsets of the unsorted input file on the BAS device. This will allow us to pack in more number of keys into the DRAM because the pointer sizes are much smaller than the values itself. This will also allow us to reduce the number of writes written to the BAS device during the end of the run phase, and can in fact sometimes avoid writing the run phase altogether if all the keys and the pointers fit in one go. And later, we read the values by performing random reads during the merge phase to generate the final output. There are 2 variants of this. One is the WizSort one pass, where the keys and the pointers completely fit the memory. The second one is the WizSort merge pass, where the key and the pointers do not fit in the memory and we'll have to do a merge stage. While the key value separation allowed us to take advantage of the byte reducibility, random read bandwidth, and the asymmetricity of the device, we still need mechanisms that will allow us to be interference aware and device constraint concurrent. Now let's look at a naive way of doing sorting concurrently. Here you have a no synchronization mechanism where you have each thread performing reads, sorts, and writes independently. These independent threads have no way of controlling the amount of concurrency per operation, and in fact straggler threads can cause interference between reads and writes, as shown here. Now, in our system, we use a thread pool controller to estimate the number of concurrency per operation by doing micro benchmarks previously, and we use an interference aware scheduler to make sure that the reads and writes are never overlapped at any given time. This will act as a good deterrent for interference effects, and in our case we use buffer to act as a logical barrier between 2 different kinds of operations. Now let's put all of this together and see how WizSort one pass works. One pass is the version where the keys and the pointers of the entire unsorted input file fits into memory at once, thus avoiding the need to do merge phase and doing intermediate run file generations. So we first perform a random key reads into the DRAM and maintain pointers that point to the values. Once we have the unsorted index map, we sort it and then gather the values dynamically from the unsorted input file on a need basis and fill the write buffer. Once the write buffer is full, we write it to the sorted output file. We repeat this step until the sorted output file is completely generated. Similarly, WizSort merge pass, where the keys and the pointers do not entirely fit into the memory, must now make a merge phase to produce the final sorted output file. Here, just like before, we gather the keys and the appropriate pointers to the index map, sort it, but this time we write it back as run files to the BAS device. We repeat this step until all the run files are generated. Here, much longer runs are generated because more fit into the memory. Longer runs will help reduce the number of passes as well. Next, we gather the keys and the pointers to the read buffer to find the minimum key. Once we find the minimum key, we at the same time gather the value from the input file and write it to the write buffer. Once the write buffer is full, we write it as to the sorted output file in sequential manner. We repeat this step until the final sorted output file is generated. To evaluate WisSort's performance, we broadly ask the following questions. What is WisSort performance on sorting benchmark? Does WisSort actually utilize the braid device effectively? What is the benefit of the concurrency optimizations that we have introduced? How does the benefits vary with different key value ratios? Does strided gather always make sense? How does WisSort perform on different braid devices with varying characteristics? Does WisSort's mechanism always work well with different properties? Now, although we answer all these questions in great detail, we'll only be focusing on the concurrency optimizations in this talk. For the rest, please refer to the paper. In this graph, on the y-axis, we can see the total execution time in seconds, and on the x-axis, we can observe external merge sort and WisSort with different concurrency strategies. The no-sync strategy uses read sorts and writes independently, thus not being aware of interference or the device constraint concurrency. The I/O overlap strategy is aware of the device constraint concurrency, but still overlaps reads and writes to maximize CPU usage. And the no I/O overlap version separates both reads and writes and is aware of each operation type concurrency. Thus, it's aware of both I and D properties. And on top of each of the bar, we can see the properties that each version is compliant with. Here, we're sorting 400 million records of 10-byte keys and 90-byte values. The first interesting observation is even existing block-based solutions can be made fast by making it simply concurrency aware. Right. Here we see 26% improvement of external merge sort no I/O overlap compared to no sync. Next, even more interesting is when we take WisSort, which is WisSort no sync, which is BAR compliant, and compare it against a block-based approach, but it is concurrency aware, we see that the block-based approach is 13% faster than the byte addressable based approach, which is not concurrency aware, emphasizing that I and D properties are more important than the B and A and R properties. Finally, being concurrency aware while exploiting byte addressability and random read performance can give up to 50% improvement, thus showing that being compliant to the all 5 properties will give the most optimal performance possible. Finally, let's generalize the braid model for it to be applicable to all data-intensive applications. Applications must be aware of the byte addressability aspect and reduce I/O amplification where possible. Applications must take advantage of the higher random read performance by avoiding redundant reads. They should be aware of the asymmetric read-write cost and trade more reads for fewer writes when possible. The read-write interference is an interesting character, and applications must avoid scheduling reads and writes at the same time. Finally, the device constraint concurrency must be taken care of by managing access concurrency per operation. In summary, we showed that conventional access strategies are suboptimal for data-intensive applications. So we introduced a braid model and showed how complying to the braid model provides peak performance. We introduced WisSort and 3 mechanisms: key value separation, interference-aware scheduling, and thread pool controlling, and showed WisSort can perform 2 to 7x faster than state-of-the-art approaches. Thank you.